Okay, good afternoon, everybody. My name is Pablo Mendoza. I'm a professor at the Department of Civil Engineering at Universidad de Chile, and it is my immense pleasure to introduce the first speaker of our Water Resources and Environment webinars for the spring semester 2022. Okay, so today I have the mission to introduce Dr. Lucia Scaff. Lucía is a civil engineer, and also she holds a master's degree in meteorology and climatology from Universidad de Chile. Lucía also got her Ph.D. at the University of Saskatchewan in Canada in 2019. Since then, she has been working on hydrometeorological studies using high-resolution atmospheric models. Dr. Scaff is currently working as a postdoctoral fellow at the Water Research Center for Agriculture and Mining in Chillán. So today, Lucía will be talking about hydrometeorological applications of regional climate models at convection permitting scales.
Thank you, Pablo. Okay. This is not working. There it is. Okay, so climate change has pushed improvement in atmospheric modeling. One of those advances is related to our capacity to better simulate a higher spatial and temporal resolution in the atmosphere. And that's a critical step forward to be able to explain heterogeneous patterns of the climate change impact in the atmosphere. This new stage of models need to be assessed with accurate observations, and that's to understand better their strengths and weaknesses. With that kind of information, these new model outputs, we can characterize mesoscale processes and it changes in a warmer climate, and also provides tools to impact studies in different earth sciences, such as hydrology. So I will briefly describe what a global climate model versus a regional climate models are. The global climate models represent the largest earth systems. For example, the atmosphere, the ocean, their interaction with the sea ice and the land surface. Those models are run in a coarse resolution, and that makes it possible characteristic make them possible to run for many simulations, and that gave us the uncertainty range that we see in climate change projections. Right, the main international coordinated project to standardize this kind of simulations is called CMIP. Now it's in phase 6. On the other hand, you have the regional climate models, which are area-limited models that are run using global climate models as a boundary or and initial conditions, and that can also be run using reanalysis data, for example, or a combination of both. I will show you later on an example of that case. Those kind of simulations are higher in resolution, in time and space, and that give us more detail to study the atmosphere and the land surface processes in a mesoscale, so in a regional scale that you can see the topography and differences in the land surface, the land use, etc. The main international project that coordinates this kind of simulations globally is the CORDEX. That's the reference if you're interested to see more about that. Here I'm showing you an example. This is an animation of a regional climate model and a convection permitting scale. So when the simulation is run at 4 kilometers or higher, we call it convection permitting scale because you can resolve convection in the equations. You don't need to parameterize it. And that's that visualization. You can see the clouds there, a couple of cross sections. I'll run that again. This is a simulation in Canada. The mountains, you can see the mountains here in the, I don't know if you can see the mouse online, but it's there. The snow is there. This cross section, the blue and yellow one is the moisture field. And then you have vertical velocity in red and blue. So all those kind of details are there, and it's a lot of information that we can use to do different types of studies. I will show you 3 examples later on. Another way to see regional climate models versus global climate models will be using this plot. So we have vertical axis, the spatial scale, and the temporal scale in the horizontal axis. And in squares there, you can see different atmospheric phenomena. Global climate models sit on that part of the plot. So it normally able to resolve cyclonic, synoptic cyclones and the general circulation, and it goes up to 100 years. And the upper part of the plot shows a more human readable numbers for the time. So 100 years for global climate model is something that you can find available online. That's very useful. The CMIP6, the last stage of this coordinated project, push this boundary to higher spatial resolutions to up to around 50 kilometers. Some of them are trying to run this long-term simulation of 25 kilometers, which is a great advance as well. Regional climate models, on the other hand, is covering another part of this plot. So we have higher resolution. And that means not only just running the simulation or the model and in a finer bit cell, you need to resolve the atmospheric and the land surface processes on those scales that start to make more sense at that type of scale, so tenths of kilometers. The convection permitting simulations, it goes even farther to a kilometer scale. But I haven't seen anything like farther than a 20 years simulation with this kind of configuration. But as I said before, we need then to represent other processes to make these models, valuable enough to produce the atmosphere, reproduce the atmosphere and the land surface at those scales. So especially for hydrologists, it's very important to remember that even though this is a climate model, the module that does most of the land surface interaction is the land surface model. And that's where you find all those processes of runoff, generation, snow, accumulation, melt, etc. And the canopy interacting with that. This is one example. This is the NOAA-MP. It's a land surface model used in WRF. WRF is a weather research and forecasting model, which is very popular in the US and in Canada as well. And this is a diagram of which processes they are including now in this NOAA-MP. This parameterization or the land surface scheme is using WRF in convection permitting scales, and it considers many processes. Here, I will show you a couple of them. So it's one layer of canopy, which is a tree there, that can interact with rainfall, snowfall. So you have snowfall interaction by trees. The snow on the other side have 3 layers, the very thin one at the top, which it's very important to really account for how is the interaction between the atmosphere, the boundary layer, and the first layer of snow. You can find a refreezing process, liquid water through the snowpack moving on. You have the unconfined aquifer at the bottom of this diagram. That is also very important to drain water in case that is needed. And that's an advance as well. So yeah, that's an idea that is very useful for the hydrologist who wants to work with global climate models or regional climate models projection in the future and know how they are really representing all of this. I will show you now 3 examples of my work as a Ph.D. and postdoc. The first one was about assessment of the performance of the convection permitting model to see how the model was able to reproduce the diurnal cycle of precipitation in North America. That was published in 2020. So this work started with this motivation. So the regional climate model, when you parameterize convection, it gets the convective storms wrong. The main characteristic that you can find on the literature is that the precipitation intensity and the diurnal cycle, which is very characteristic in summer precipitation, it wasn't there on regional climate models, and not even in global climate models. So that's something that convection permitting simulations are able to overcome. And why is that important? Is because those characteristics are key features that we look into when we try to forecast floods, for example, especially in the mountains. In the Rocky Mountains in Canada and the US, at the lee side, you have these convective storms in summer that can be very intense, and they produce flash floods or floods itself. So this is one example of the previous literature in 2014 that I'm showing you here to introduce this concept of diurnal cycle. So what that means is that precipitation has a preferential time during the day to fall. Okay, so this is the afternoon peak. You see that the black line, which is observations in this plot, has a maximum around 5 p.m. And then the other two lines, the red and the blue, are models. The blue one is a regional climate model that runs at 12 kilometers with parameterized convection. And that's, yeah, it's clear that it cannot capture that maximum during the afternoon, right? And then the other simulation in red is the convection permitting at 2 kilometers, and it got it right. So that's what I was looking at in North America. This is the study domain. This is the model I was using, all that topography, the region that is with the topographical surface there. And those black dots are all the weather stations that I used to validate this model. That was around 2,900 stations at hourly time step. I need the hourly observations, right, to get the diurnal cycle. More details about the model. This simulation was performed in the cameras off. Oh, that's good. So the simulation was run in two scenarios. The first one is historical simulation, that I call it control, that use era interim as a boundary condition. And then the future simulation uses this approach, which is a pseudo-global warming, that considers a combination of a reanalysis, era interim, plus a perturbation taken from global climate models. Besides the observations, which was those are black dots, I also use this radar product, which is a gridded data at 4 kilometers in most of the US. Stage 4 is the name. And this is the last square on the bottom left, show you how I characterize the diurnal cycle. So I use the harmonic equation, and I consider now the phase and the amplitude as indexes to explain the diurnal cycle. So now I will show you the phase. The phase is the timing of this maximum precipitation, which is in hours, and here has many colors. So the observations is on the left, and stage 4, which is the gridded data from radar information, is on the right. The main characteristic here in the US in summer, because this is in June, is that precipitation has an afternoon peak in the intermountain region, which is the red colors around here, and in the east, okay? And then you have this interesting pattern in which you have night peaks in blue, yeah? So hours around 22 hours and 0. And then it moves to the light green. That's called the eastward propagation of storms in the US. And that's something very important to capture to be able to represent these storms in the model. This is how the model looks like when we calculate the same phase of precipitation. So it's mainly, you have the afternoon peaks, so the main pattern is there. And something very encouraging as well is that you see the night peaks as well. And that's the model was able to propagate the storm to the east. However, the early morning peaks, which are light green in the observation at stage 4, it's not as strong. That's so after that, I will show you how this really the diurnal cycle looks like in this region. So for that, I cannot just mix everything because every place has a different diurnal cycle. So I took all the stations at the east side of the Rockies that has afternoon peaks, which are those red dots. And I plotted in the upper plot the diurnal cycle of the observations on stage 4 in black and how the model looks like in purple. So the peak, the timing is right. The magnitude, the amplitude is kind of overestimated. I did the same with the rest of the stations on this region, and the eastern propagation is a thing. So the night peaks is there, and actually the model performs very well on that group of stations and that area. And then when we move to early mornings and late morning peaks, the magnitude is there, so it's not very bad, but the peak, the timing is kind of wrong. With that in mind, it's kind of a performance assessment, right? How the model is really capturing this. We study and we analyze the climate change impact effect in this simulation. So here I'm showing another month. This is May. On the right panel, you see the control simulation, historical simulation in purple again, and then orange shows the future scenario. So we have an amplification of the precipitation amplitude consistently during the day. And that is something that we can also see in the map here. So it's the precipitation amplitude is in percentage increase, overall increasing. Can you see the map there? It's US on the background. So besides that, I also included these black circles, which are the statistically significant ones, where the difference is statistically significant, and it's mostly in Canada. So after that, we decompose precipitation in precipitation intensity and frequency to see where is really this changing happening. So precipitation intensity is on the bottom center part, and it's overall increasing with many regions where that difference is significant. Meanwhile, in frequency, we see this dipole where in the US, we see a decrease in frequency of the storms. However, in Canada, is increasing. So in the US, you get storms that the magnitude is increasing, following by the intensity, but frequency is not there. So it's probably something that you can call a more extreme events, more intense and less frequent. While in Canada is more intense and more frequent. With this data set, then we decided that we have the advantage to study a mesoscale process. And here I will talk about the dry line. The dry line characteristic in North America, dry line is a mesoscale feature that is related to the convective initiation. So how convection initiates, it's a very complex process. And one of the features that can produce that initiation is the dry line. The dry line is a strong moisture gradient that I will explain a little bit more afterwards. That was published in 2021, and it was also highlighted by the Nature Climate Change in the same year because of the importance of bringing this kind of mesoscale features that are normally used in the forecaster community to the climate community. This is a climatology of humidity in the region during summer, in June. The 13 years average using the same model simulation that I explained before. And it's clear this is a strong gradient, right? You have moisture coming from the Gulf of Mexico from the south, and then a drier and hotter region on the west. When this moisture gradient is strong enough that is happening in some places, it's not all over the continental ones, but happens in some places, it produces an imbalance in the atmosphere that has to be counteracting, in this case by the solenoidal circulation, which provides the environment to increase vertical velocity and produce convective initiation. This is the model, again, the same one in Canada. The drylands are also a feature in this region to initiate convection. So we see clouds in white, in blue is the moisture field, and then I will show you one convective cell that is initiating right at the lee side of the mountain on the dryland region. How that is very clear in the model. These lines, yellow lines, are back trajectories. So you see the convergence of air coming from the west, from the surface and north, and then moving to eastward. There, I'm highlighting in red the vertical velocity right where the cloud is forming, and precipitated water in that light blue colors. So this example was in July 2013, and I will show you how when we want to quantify this, we need more accurate calculations and maps. So this is a map of this event. This is the specific humidity zonal gradient, and it's a very strong dryland. That's why I chose this example. And I am plotting here a cross section close to a Rocky Mountain near Saskatchewan River Basin. It's quite north, it's 52 degrees north. And on that cross section, you can see the field, the moisture field again in colors. So a strong gradient is right there at the foothills, and then the winds is narrow, so convergence region is right where the moisture gradient is, as we can expect. And then black contours is vertical velocity. So the model gives us hourly time steps. That's very, it's a lot of information to see the evolution of these events. I'm animating both at the same time, but you can see how these clouds are forming there, precipitation in blue contours are appearing, and then how these, let's try again. There it is. So the dryland is moving across the foothills as well. That's a characteristic feature they have when it's occurring closer to the mountains. How those convective cells are forming and moving to eastward and organizing is also something very common in this kind of storms. So we decided to evaluate the importance of these features, the drylands, in the entire domain. For that, the simulation is 13 years in our time scale. So we decided that it has to be automatic objective identification of these features. We use a multi-parametric algorithm to select these events in 4 parts of the region. I will show you the map later on, but that's something very challenging. Even nowadays, it's really hard to objectively identify atmospheric boundaries, something that is hard for frontal systems, for other type of boundaries like dry lines, outflows, etc. And I'm here highlighting 3 papers that are working on that using artificial intelligence as well. In this case, for frontal system, which for us, it sounds like something a synoptic scale, which is very defined in the literature. But when we bring that to an actual algorithm to identify them, it's hard to get accurate results of what an experienced forecaster will find. And that's a challenge. Anyways, we did the experiment and we ran these 4 separate subdomains across the simulation. And this is an example of how the algorithm select the dry line. So the contour, green contour is where we identify the dry line as an elongated feature with a meridian gradient with certain characteristic in the moisture field and temperature. With all that information, we create composites to show a climatology of how a dryland looks like in the domain, in the entire region. And that's how it looks like for the historical simulation on the left and the future simulation on the right. And that's the difference. So you see that there is an increase in frequency of these kind of features on the region. I left this particular map. If there are many things happening here. In Canada, you have a strong hotspot of very frequent dry lines, which are under studying. They are studying that kind of features there. And then you have this region in the US that is very well studied and is very dispersed, less frequent as less narrow to one region, but spread over the central US. And then in the south, you have this strong region of relative maximum of frequent dry lines, which is very, it's for a discussion. It's discussed in the paper as well. Is it really dry lines as we define in other regions, or is this more related to sea breeze circulation? Probably both. We analyze this climate change impact in drylands in a seasonal scale. So this is month in the horizontal axis. I'm showing the magnitude of the dryland and see how that is increasing in the future. We have the historical simulation in blue again, and the future in red. So it's mainly increasing in both in these two regions. It's also interesting to see how the seasonal maximum is in a different month. In the US, you have the maximum of the magnitude of drylands at the beginning of summer, which is related to the low-level jet maximum that is occurring from the Gulf of Mexico to central US on the same months. On the other side, in Canada, the maximum is occurring in the middle of summer. It's the same behavior for the dryland, the major axis of the extension of the dryland. They are getting more extensive. What I show you here in gray squares is the statistically significant differences. An analysis of the diurnal cycle of the dryland magnitudes is presented on the right. And something interesting here is, as we expect, also increasing in magnitude, is that the magnitude of the dryland in the early morning peaks in the southern US, so I'm talking about the bottom right panel, the magnitude represented on these red bars are quite similar to the magnitude we had in the historical simulation for the afternoon peaks, where the maximum precipitation is occurring. So that's something really concerning to see how those kind of more frequent drylands and more intense will initiate convection maybe early in the morning in the future. That's for future research. So that's something we are hypothesizing, but we haven't done that kind of analysis. So the conclusion of these two parts is that we have this regional climate model and convection permitting simulation that really give us tools to analyze summer precipitation in a more reliable way, and it can be used for diverse applications. You can do study impacts of extreme events on summer, and that's something that is very valuable. The diurnal cycle is amplifying in the future, and it's mainly producing more intense and more frequent storms in Canada, and only more intense and less frequent storms in the US. As a number here, I can tell you that the dryland, the diurnal cycle is getting more intense in Canada. Sorry, I got lost. Okay. The drylands are also more strong and more frequent, and that's something that will be related to the diurnal cycle change, that the diurnal cycle change of the dryland that can impact the convective initiation. The last part of this study is ongoing work that it's about how climate change is impacting winter warm spells, which are kind of heat waves in winter, and that impacting the snow ablation in the Western North America. So it's more hydrological impact study. So why winter warm spells? They are increasing in frequency and duration in winter time. These historical trends I'm showing here. So it's statistically significant in the central US and Canada, and we expect that to continue in the future. So we see the need to quantify how this winter warm spell will impact the snowpack. because if those extreme events are increasing and the snowmelt volumes are decreasing as well for this reason, it will be critical for water resources. So as a definition here is equivalent to what we see as a heat wave. We see a period of 3 consecutive days, which the daily maximum temperature is above the 90 percentile. In a moving, that 90 percentile is a moving average of in each day of 15 days window. This is an example. It's a time series of precipitation, daily maximum temperature. And in red, I'm showing you these winter warm spell events. And now I will show you the study domain and an example how I relate these winter warm spells to the ablation. So the domain is part of the domain I showed you before, is the western side of the region, in which the mountains has significant amount of snow in winter. The way we have to identify those regions of significant snowpack is separating the pixels that has snow water equivalent above 150 millimeters. So it's mainly highlighting the foothills and the peaks. And the example here is taken in California in the Sierras. It's 1 pixel, and in this graph, I'm showing you the same daily maximum temperature in black, the winter warm spell events in red, and then the snow water equivalent in blue. So we see how the snowpack evolves and accumulate during the winter, and then we have this particular winter warm spell event, which was synchronized with a decrease in the snowpack, and that is what we call ablation. At this stage, we know that ablation is a loss in snow, and it's sum between sublimation and melt. It will be important later on the presentation. I will explain you why. So the first question is really winter warm spells important on those kind of ablation events? Here with this simple experiment of calculating ablation rate in this case, so the rate that it is losing snow. In the event of winter warm spells in the center, and on the left, the no winter warm spells day. At first sight, you see that the rate, the ablation rate is higher during winter warm spells. And when we move that to a probabilistic density function, we clearly see that values. So the difference on the 50 percentile of the median of those two distributions is around 41%. So these events are occurring, these winter warm spells are producing more intense or higher ablation rates. That's the main message. In the future, first we look at the domain again, and we see that in a warmer climate, we get less pixels with this characteristic of having snow water equivalent above 150 millimeters. It's a little bit more than half of the pixels that stay there. But we use those regions, and we calculated again the ablation rate and the total ablation, because annual ablation, it calls you for the amount, the total amount, right? Ablation rate is the speed that the snow is losing. So here I'm showing the same colors. This historical simulation in blue and the future simulation in red. And in both cases, in the future, the rate is increasing, and the annual ablation is increasing as well. Ablation rate increases around 33%, and the total ablation is higher, it's around 41%. If you remember the maps, there was a lot of variability through the region. So we divide the domain in 4 climatic regions, we call it. We use the average air temperature and humidity to separate this region. The maps of air temperature and humidity are on the right. We use the average there, so around -7 degrees and 2.3 grams per kilograms of humidity, or water vapor mixing ratio, to be precise. And then if you take all the pixels below that median temperature and below that humidity, we found that region, which we call the cold and dry environments. And when we do the same with values above those averages, we found that region in orange, that is a warm and humid environment. And then you have the combination of both, like cold and humid environment and warm and dry environments, but they are smaller. Is warm and dry environment is clustered in the southern part of the Sierras. And the other group is in the upper part there, cold and humid environment. Oops. And that's the distribution of the point. So the domain is mainly clustered in cold and dry environment and warm and humid. So we calculated the ablation rate and annual ablation again on each region to see the differences there, to understand these processes better. Here is the cold and dry. So the Rockies, the interior part of the continent in the upper panel, and the coastal mountains in the bottom panel. And you see the differences there, right? The ablation rate is changing quite more significant in the warm and humid environment, which is probably because it's much more sensitive to ablation due to a snowpack that is closer to 0 degrees and ready to melt in the middle of winter as well. So the changes are quite different. It's over 100% in the warm and humid environment. And there I'm highlighting there that the regions in the coast were more sensitive to warmer temperatures. So this is the part that I will explain a little bit more about this difference between sublimation and melt. Why we care about separating the ablation? It's because sublimation is lost in the atmosphere, but melt is something that we potentially can store in reservoirs. So it's important to make the separation, to know that even though the water is melting, it might be touched downstream. Here is the same. Here I'm showing the total sublimation, total melt, so in millimeters of the snow in both the scenarios again. And both are increasing. It's important to notice as well that sublimation is around 11% of total ablation. So it might be significant or not, depending on the study or what you're looking for. But it's around that number. And that percentage, around 11 and 17%, it's keeping the same numbers in the future scenario. So we're no change in that distribution between sublimation and melt. This is the last result on this study, is about how ablation can be related to elevation. We are working on that. So we see some more sensitive snowpacks in the upper part, in the higher elevations, and that's very clear in warm and dry environments. So we are looking into that. What could be the reasons? Those kind of a relationship with elevation. It's something that we also see in warmer spells. If we see changes in the future of the warmer spells, they look like they have a stronger change, more intense changes in the future. At higher elevations. So conclusions here. We found that ablation rates are more important during high temperature level or winter warmer spells. And there are substantial changes in the snowpack. We have winter ablation and ablation rate increasing in the future, especially over the coastal mountains, and they vary with elevation. So that's all about my study. I included this slide about a convection permitting simulation that is being produced here in South America under the Research Application Laboratory at the NCAR. It's a database that is being stored there and is available to the researchers. You need to register and talk to them, but they are very open to share this with everyone who wants to develop studies in this region. The historical simulation is done. It's 22 years of this simulation at 4-kilometer resolution, a convection permitting scale. And it was run with the ERA 5 reanalysis. If you need more details, well, you can find that webpage online, and I can give you more details or the contact if you want to access that data. Some more general conclusions here. What I want you to take home messages is that regional phenomena convection permitting scales, it's a very valuable, produce very valuable information for hydrometeorological studies, especially in places that we don't have even like any measurements. So that's something that we should take advantage of. Anyways, we need a substantial team effort to be able to create this kind of simulations and post-process analyze this. So it's a teamwork, and it's an international teamwork effort that we need to work with this today. Something that I didn't mention before, but it's something to keep in mind, is those simulations are expensive computationally, and it's hard to store them for a long time. So you cannot just reproduce many realizations as we do with global climate models. So it limits the uncertainty analysis of climate change projections. Yeah, and the last point here is highlighting that we have the simulation in South America, but it's very important to validate that in places like here, that we need more observations, but we have some, and we need to do that step before any further studies. Thank you.
Okay, thanks a lot, Lucia, for accepting our invitation and for sharing your exciting research with us and for coming in person. So for those who don't know, Lucia traveled by train this morning, very early to be here. So we really appreciate it. Okay, so we're open to receive questions from the audience here in Santiago de Chile, or from anybody who's connected on YouTube. Please feel free to make questions. Roberto?
Lucía, thank you for the presentation. Very interesting, all your work. I was wondering on the pseudo global warming experiments, because I believe that I'm not sure if this is the way you do it, but I believe you change the atmosphere in the reanalysis by the amount that you see in the projections. Somehow you add temperature maybe, or moisture as well. My question has to do with the uncertainties in in things like ablation. If you look at projections very far in the future, say the end of the century, probably the ocean also has something to do, and that will not be included in the pseudo global warming. And if you think on ablation, maybe near the mountains, I would think that it depends heavily on the surface relative humidity and also on the wind. So how do you see those uncertainties playing out in the models, and is it something that you would like to do with maybe a couple model in the future, or with more simulations with different models?
Yeah, it's something really hard to address, like to assess that kind of changes, right? Because we are not doing many realization of that at that point in science. But the pseudo global warming, we know the good part is we know the limitation of that approach. We know that is only considering the thermodynamical changes in a synoptic mesoscale, but we don't have the ocean temperature changes. We don't have changes in the tracking of the storms entering into the continent. So it can be way drier if the storms are moving northward, right? And that's something we are not looking at here. So it's something that I'm not not gonna pursue, but it's a very good research topic, right?
Thanks, Lucia. Any other questions from the audience here? Or any other questions?
I have your question from YouTube.
Okay.
Okay, so Miguel Lagos is asking if did you evaluate the land surface simulation of snow processes with observations?
Should I repeat the question? I don't know if online you can hear that, but okay.
Okay. Did you evaluate the land surface simulation of snow processes with observations?
Yeah, so Miguel Lago is asking if I validate the snow of the model with observation in the region. I did not do that, but this simulation has been studied by a big group, and they have done a good validation of that with using snow tells in the region. So there are a couple of previous studies with that, Miguel. I did some validation on the winter warm spot, the atmospheric part. So that will be in the paper. And yeah, the main pattern is quite there. There is a cold bias in the model that is also published before by the by Changhai Liu, who documented this simulation.
And there is another question. What do you recommend for weather simulations in Chile?
Like climate simulation, I think. They're asking what climate simulations we can use here. At this resolution, at 4 kilometer resolution, I'm not sure if you find a regional climate model. Is there anything?
There is, yes, the REC-CM at CR2 has 4 kilometer resolution.
REC-CM at the
CR2.
At CR2, yeah.
Dennis was good perform some regional climate model simulations, but one boundary condition and one model.
Okay, so Roberto Rondanelli, who's here in the audience, he's helping me with the question. He knows that the CR2 with Dennis Boscourt, he's producing this simulation at 4 kilometer resolution. It's one realization with one scenario, but it's there. How many years do you know?
It has, I think it has until 2050. So it's historical plus,
okay.
plus projection.
Okay, so the historical and one projection to 2050. And then the other model that I showed you before, at the NCAR, that's available. That's 4 kilometer resolution in entire South America. The historical simulation is done, and the future will be until 2100 years. Will be a mission scenario of 3.7. It will be a SSP 3.7. That will be ready next year. Those two. We have something here.
Okay, we have something. That's good. Okay, thank you very much. Any other questions from YouTube? No, not yet. Okay, I think here. Well, I have a more philosophical question, because all the results that you have shared with us, which are very, very exciting, at the same time depend on a lot of assumptions. For instance, the PTW approach, you apply this change arising coming from a GCM, right?
Yeah.
And the same thing with the horizontal resolution, you apply 4 kilometer resolution, and you also rely heavily on a land surface scheme, ONP.
Yeah.
So the question is, after doing all this work, where do you think that we should put more attention?
In those steps?
In all the steps in your modeling chain. What is that step that you think is more important to be more careful about?
Yeah. I think we should start from the beginning. For me, the beginning is the observations. The observational data set. Actually, there are a couple of papers in North America that we think that, well, they have a larger network, but still this kind of simulation sometimes outperforming the observations over there. And that's something that we should take more care about, because even though observations are one location in the map, and it's a short or a small period of time, and all that, and it's not in the future, of course, those are critical to all what we are doing, to start like diagnosing and saying, well, the model is performing well, or we are losing so much uncertainty on the global model that we are creating so much uncertainty on the first stage of using a global model to simulate the 4 kilometer resolution. We need those good, reliable observations. So that's the first thing I will solve. Yeah, I'll try to solve. Okay. And in the modeling stage, I think land surface models are doing very well. I haven't evaluate them in detail, but I really like what they are. I will trust them a lot. The future scenario is, even if we do 100 of those realizations, we can evaluate the uncertainty, right? But it's still the future. So yeah, we'll center everything from the beginning.
Okay. Cool. And speaking of observations and models, do you think, or anybody in the audience, do you think that we got into the point, or we're getting to the point where results from this kind of model, convection permitting numerical models, can be more reliable than in situ stations in measuring precipitation in mountainous regions?
It does. You know what? It surprised me a lot. In the US, you have these thunderstorms, convective storms that are very, how you say that, localized, right? And if the station is right next to it, it will not capture it. But radar information, for example, that it could be called observations or model, I don't know. That is something I feel it's in between. It matches way better with the simulation, with the continuous field of convection permitting simulation, that the observation. That's something that we can understand. So it is possible that it is reproducing the fields better than observations in some places.
Cool.
You know, the observation is not right there, but that's an advantage. Producing that in places in storms like that, or remote regions in the mountains that you have no chance to measure. Yeah.
Right.
I like those models. Yeah.
Okay, so if there are no further questions, then we want to thank you again, Lucy, for being here.
Thanks for inviting me.
And I also want to thank everybody who's here right now and also have joined us on YouTube. And I want to remind you that this is just the first of our Water Resources and Environment webinar series that we will be broadcasting on YouTube for the rest of the spring semester, spring in the Southern Hemisphere. And the upcoming speaker will be Professor Rosanna Newpower from the University of Colorado, who will be speaking about recent advances in estimating stream depletion. And that will be on September 1st. So put it on your calendars. So thank you very much and have a good afternoon.